Hello everybody and welcome back. In our last class we were talking about exponentials and logarithms. Exponentials, if we recall, were this idea of kind of exploding and exploding, dividing repeatedly or multiplying repeatedly, so that we had this grouping where we had a large growth or quick decay process. And we could think of this as sort of like the movie Pay It Forward. The movie Pay It Forward is founded on this idea of saying you can go out and you could help 3 people, and then they can pay you back by helping 3 more people each. So the first time you've helped 3 people, but the second time those 3 people help 3 people each, which gets you 9 people who are helped on that second turn. And then they could go out and help 27 people, and this begins to explode pretty quickly. In fact, if I were to ask you how long you think it might take for this process, this Pay It Forward movement, to help out everybody in the world, how long do you think it would take? And it's actually a lot quicker than you'd think. There's about, 7.5 billion people in the world, and as it turns out, this Pay It Forward movement would actually help out everybody on the planet in less than 1 month, less than 30 days. So in less than 30 of these iterations, this movement blows up so quickly that it would actually circle the entire globe. Now, logarithms are our method of trying to capture this quantity. So if I asked how many times does it take for this movement to circle through the globe, we could say the logarithm would tell me exactly how many of these iterations it takes. It takes less than 30, so the logarithm would turn out to be less than 30. So in other words, logarithms are kind of our power finder function. They're trying to figure out how many of these powers would have to occur or how much of this repeated multiplication would have to occur for you to get to a desired result. So let's look at a couple of examples and refresh ourselves. So let's do a few of these ones here, and we'll start with some easy ones as a nice little refresh. So let's change the following from an exponential to a logarithmic form, and I'm just going to do a few of these ones, and you can do the rest of them. So we're talking about an exponential to a logarithmic form. Well, whenever you see a logarithmic anything, you can actually cross that off. You can just call this a power finder, and you can do this in your notes. Power finder function. This is an informal way of thinking about it, but I think it means a lot more to our intuition. So we can think of, what would I do here? Well, I'd be trying to find the power that would take 2 and raise it up to 8. And sure enough, that would be 3. So if we wrote that in our traditional way, that'd be logarithm base 2 of 8 equals 3. And the story we would hear is that there are 3 kind of explosions of 2 that would happen in order to get to this 8. So this would be our nice little answer here, written in logarithmic form. What about for this one here? We're saying, okay, what's our power? We're trying to find the power. The power here is obviously going to be -2, so we're trying to find the power, and it's the number of explosions that take 5 up until 1 over 25. So we can say, okay, let's do our power finder function. We're trying to take 5 and explode it up to, in this case, I guess kind of collapse it down to 1/25th. And sure enough, that would be -2 would be the power that causes this all to happen. That'd be our power finder function did in fact find us a power. That's great. And so we could write this as saying log base 2 or log base 5 of 1 over 25 is equal to -2. Okay, excellent. So that's a nice little way for us to think through it. What about changing logarithm to exponentials? Well, again, we're saying that this logarithm is really just a power finder function. It's finding the power of raising 3 up till 81. So sure enough, 3 to the 4th, 4 explosions of 3, 4 iterations of that Pay It Forward movement would get you all the way over to this 81. And so we can try that out with the other ones. I'll actually try the hard one here. This would be, a power finder. So I'm looking for a power. 2 would obviously be my power. And it'd be, I would take 3/5. I would raise it up to 2. So it's still my base of 3/5 raised to a power of 2 is equal to x. And there you have it. So how do we use this to solve some logarithms? Well, if we look at this as a story, then again, this says that the power that causes 7 to raise up to x minus 1 is the same thing as the power that causes 7 to rise up to 12. So that means x minus 1 must be that same power of 12. And sure enough, that would be x equals 13. We could check this by just plugging it in up here. That'd be log base 7 of 13 minus 1 would be equal to log base 7 of 12, and sure enough, that looks like it works out just perfectly. Now, I like to use this idea of a logarithm or a fake logarithm as a way of building up the intuition for what these logarithms are actually doing. As we said, they're counting the number of iterations, the number of explosions you have. They're counting that exponent. They're seeking out that power finder. But I like to use the logarithm. So if we recall, the logarithm was this idea that if I gave you a number that was, I don't know, some power of 10, we got 10 or 100 or something else like that, that a logarithm was just going to count the zeros afterwards. So for example, if I did the logarithm of 10, it would find 1 0 here and it would spit back the number of 1. And I could say, okay, what's the logarithm of 100? And I'd count and see 2 zeros, and that would get me the value of 2. And we could even kind of extrapolate this pattern backwards a little bit. So we could say, okay, what if I did just the logarithm of the number 1? Well, I don't see any zeros, so I guess that would be 0 of those kind of magnitudes in there. And I could even kind of do it backwards, where I say, okay, what if I start taking it backwards a little bit, and now I'm looking for 1 before the decimal point? Well, that would be -1, right? Because if I'm looking at this pattern, we can kind of flow it down, where 100 was 2, 10 was 1, 1 is 0, 1/10 or 0.1 would be -1. The logarithm of 1/100th would be going 2 backwards in our pattern, so we could call that a -2, etc. But when we say this logarithm, this is really nothing more than my way of trying to get us comfortable with the idea of logarithm base 10 or log base 10. One of the most common ways that we count with logarithms, at least in the Western world. And so what we're doing here is nothing more than counting the number of explosions, the magnitude of a number. And so we could actually use this exact same idea, saying, okay, well, what if I have like log base 2 of 8 equals 3? Like, let's take a look at what that actually means. We could be counting the number of zeros that are in log base 2, but maybe that's easiest done in the same way that we normally count things in base 10. We'll use like a 10 to 1 machine, or this way of counting values. So if we recall, if I was looking at something in a 10 to 1 machine, and I wanted to put in the number 100, I could think of that as 100 of these tiny little objects all over here where each of them has a value of 1. Or I could talk about collapsing a bunch of these into 10 groups of 10 right over here. And so that would be 10 groups of 10. Or I can talk about taking all of these and collapsing all of these down so that I had one group of 100, one dot right over here for our 100s. And that's the way that we normally learn about counting when we're growing up, is that we count things individually, but then we begin to give them different labels, like counting them in tens or counting them in hundreds. So when we just now view 100 as 1, and 0 tens and 0 ones. Oh, I don't want to write those. Those will maybe look like anti-dots like I talked about in another lecture. So we're just going to look at this 1/100. This is one object here. No objects in your tens, no objects in your ones gets you 100. Similarly, if we count in just twos, binary, like computers do, this means that every time that we get a group of 2, we're going to kind of collapse it up into that next group. I could put 8 objects here. 1, 2, 3, 4, 5, 6, 7, 8. Those would be 8 things each valued 1, but since I'm counting in base 2, I could group 2 of these together, and 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 actually collapse them all into that next category of 2, and that would be 4 objects. 1, 2, 3, and 4. And in fact, you could actually do that one more time, where we grab all of these and collapse them one more time into 2 groups of 4. So that would be, in our 4s over here, we would have 2 objects. But then I could actually collapse it one more time up into my 8s, my 2 groups of 2 groups of 2. And so we'll use, I don't know, let's use blue for that. So I take all of these and I collapse them all up into here. And that would be 1 object worth 8. And this is the exact same idea. So now I've talked about 8 objects worth 1, 4 objects worth 2, 2 objects worth 4, or 1 object worth 8. But in computer language, in base 2, sure enough, that's exactly how calculators count the number of 8. Like 8 as a value to them means having 1 object in the 2 groups of 2 groups of 2, having no objects in the 2 groups of 2, having no objects in the groups of 2, and having no objects in the singles value. Because after all, just like we had up here with 1 and 10 squared, computers that count in base 2 would have 1 and 2 and 2 squared and 2 cubed. And sure enough, that helps us see exactly what the magnitude is that it took 3 of these kind of collapses all the way up for us to find the magnitude of the number 8 if we were counting in base 2. That there's 3 of these groupings that were able to happen all the way up. Okay, so that's the idea of logarithms and how it relates to other bases, is that logarithms are just helping us recognize that all we have is an amount of this grouping, an amount of this explosion, or amount of this reverse explosion, this collapsing that's happening. So let's take a look at some of these, and we'll approach them from the logarithm, but I'm just going to start calling them log for right now. And let's see if we can recognize some shortcuts that help us out with these problems. Like, for example, let's take a look at what would be log of 10 times 10,000. And we'll see if we can connect it to something easier like log 10 and log 10,000. Well, let's work through it the way we would expect to do it if I was doing order of operations. 10 times 10,000 would be 100,000. And if I asked you for the logarithm base 10 of 100,000, that's just the logarithm of 100,000, that would be counting the zeros. That'd be 5. That'd be an order of magnitude equal to 5. Now take a look over here. What about logarithm of 1? What would be the logarithm base 10, or the logarithm, or the logarithm? In this case, it'd be easy to just kind of count those zeros. This is going to be a magnitude of 1. 110 goes into 10. What about in this one right here? This would be, let's see, 1, 2, 3, 4 explosions, 4 10 groups of 10 groups of 10 groups of 10 would get us 10,000. This is a value of 4. And we start to notice that there might be a pattern here. Logarithm of these two things multiplied looks like it's going to be the addition of the logarithms individually. And that actually is a property, and it's a property of saying log base of something, we'll call it log base b for base, we'll keep it generic, of something times something else can actually be thought of as logarithm base b of a plus the logarithm base b of c. And we can take a moment and we can kind of think through again why that is. And it's because inside of here, what we've got is some increasing or decreasing in magnitude that the multiplication is having. And similar to when we're talking about exponents, all we have going on here is a recognition that I can look at the magnitude of one, add it to the magnitude of the other, and it's going to be the same as creating something different and then finding the magnitude of that different kind of combination. So use the logarithms as a way to help build the intuition for these numbers. Let's take a look at this next one. So we're going to do the logarithm base 10 of 10 divided by 10,000. What would that one be? Well, order of operations, we just kind of approach this the way that we'd be familiar with. That'd be logarithm of probably 10 over 10,000. I could simplify that to 1 over 1,000. And then I would ask myself what that is. That'd be, let's see, logarithm of 1/10,000th would be 0.001, so a 1 in the 10,000th space. And then we could do our logarithm thinking if we wanted to, this would be -2, right? Because it'd be -2 repeats of kind of counting this one backwards. Let's double check that one. Hold on. That'd be 10 to the -2nd. Oh, nope. Actually, it would be 3, wouldn't it? It'd be 3, -3 that it would need to be, because 10 to the -3rd would get us 1 over 10 cubed, which would get us 1 over 1,000. So this is a way that we can use exponents to kind of check ourselves back and forth. So sure enough, this one here in our logarithm in our backwards pattern would get us that this is going to be equal to -3, excuse me. And sure enough, we can actually count and go back and take a look here. And it was sure enough, this was 100th got us -2, 1,000th would have gotten us -3. So we've got that intuition that's starting to build here. But let's take a look at it again. We know that the logarithm of 10 is 1. We know the logarithm of 10,000 is 4. How do we get to this -3? Well, we might recognize that what we're doing in this case is subtraction. We're subtracting magnitudes by doing that division. And so we can actually have written this a little bit more quickly as saying logarithm of 10 minus the logarithm of 10,000. And this logic is actually going to work for any situation, any log base b. So we can actually get another shortcut. Log base b of, we'll say a divided by c is going to be the exact same thing as log base b of a minus log base b of c. Because all we're doing is saying if I decrease the magnitude on the inside, it's the same thing as finding the magnitudes and decreasing them. We're just changing that story a little bit in our mind. All right, what about this one here? Log of 100 squared, I'll just do that out, we'll say that'd be 100, so 4 zeros. Okay, well that kind of tells us a little bit about what's going on there. That would be 4 for our logarithm. And how does it relate to the logarithm of 100? Well, the logarithm of 100 would be 2, and here I've got 2 as an exponent. How am I connecting 2 to 2? Ooh, we might have chosen an ambiguous example here, because I don't know, maybe I add 2, maybe I multiply by 2, maybe I square it. Let's try it with another example. Let's do something like log of 100 cubed. Okay, so what's that one going to be? That's going to be the logarithm of 100 with 2 zeros, 4 zeros, 6 zeros, okay? And that would come out to be, let's see, 1, 2, 3, 4, 5, 6 zeros equals 6. So what did we do between the logarithm base 100 with this 2 and the 3 to get us to 6? And we might be able to recognize what happened. What we did here was we actually found the logarithm of 100 and then tripled it. Because after all, isn't that exactly what we did? Is we had one magnitude, double that magnitude, triple that magnitude. We tripled the magnitude. So we can actually write this all a little bit more easily as saying triple the magnitude of 1 instead of trying to grow it all to a different magnitude and then measure it. Okay, so how do we write this as a shortcut? We could actually write this entire thing as saying if I have log base b, so any base of, let's say, x to the a power, that you could actually think of this entire thing as being a times the magnitude, in terms of b, of x. So as you're kind of building these ones, try to avoid making them into rules. They will become rules, they will become shortcuts in your mind soon enough. But as we're kind of learning about these things, let's start building the intuition so that we don't accidentally make the mistake of using it in the wrong place. As we're going to see later, there are a few times that will look like they are rules that are not. And the only thing that's going to save us from trying to do that grab and smash math is making sure that we have a little bit of that intuition built up. Okay. So let's take a look at these ones here. We're going to see if some of these ones, oh, there you go, exactly what I was talking about. We're going to see if some of these ones are in fact shortcuts or not. And if they are, hopefully we'll be able to see that with the intuition. If they're not, we'll catch it with our intuition. So let's play around with this one here. Is it true, change of base formula. Let's see what happens. Okay, it initially had a base of b, and then it eventually changed to a base of c, and it looks like the b went in the bottom and the x went in the top. So there's some symmetry there that's kind of saying, okay, well, x goes into the top, b goes into the bottom, and then I can change it to, it looks like any c that pops out of anywhere. Let's see if it works. We'll try it with some of these numbers here and see if we can get an idea of if it's a true statement or not. So we'll do the logarithm base b, but we'll do it with a number for right now as we're trying to explore. Log base 4 of x, we'll make that 8, is going to be equal to log base 2 of x would be 8 compared to log base, let's see, next one is c, which would be log base 2 of 4. Okay, so let's think to ourselves for a moment. Here I'm trying to find out what the exponent is that I would need to use to raise 8 up to, or 4 up to 8. We can do a little scratch work here. 4 to some power gets us 8. Well, if I square it, that's not going to work out so well. I could square root it, that would get me back to 2, and then I know 2 can explode up to 8, so I guess I could say I could square root it first, and then I could multiply it by 3. So that would kind of get me 4 to the square root of 4. So 4 square root would be 2. To the power of 3 would be 8. That works out pretty well. Okay, let's play with that over here. Log of base 2 of 8 means what's the exponent that raises 2 up to 8? Will be there'll be 3 explosions that take place. 1 to 2, 2 to 4, 4 to 8. There'd be 3 explosions. And then here I've got log base 2 of 4. What would those explosions be? That would be 2 to the second power. So that would be 3 over 2 Oh, and sure enough, take a look. It's actually parallel to what we were seeing over here with our exponents. 4 to the 3 halves equals 8. So this change of base formula actually makes some sense. What it's saying is that if you maybe have a mismatch where your base does not work very well with the thing that you're trying to do a logarithm of, you could actually do this in half steps, where you talk about how is it that you're going to kind of portion it back to something friendly. How are you going to kind of divide it out? How are you going to root it back down to something nice? And then how do you scale that back up to get you your final answer? So that's kind of cool. Okay, change the base formula. True. Absolutely a true formula. So this one works out quite well. We can change the base if we take the base and reference it to another value. So we do a logarithm of a new base to the base on the denominator, and logarithm of the new base of the argument on the numerator. Okay, that one's a little bit odd, but maybe use the symmetry inside the formula to help us remember that one. And we can again see that what we're doing, at least visually speaking, this isn't the reason, but it's a nice visual reminder, is that we've got the base goes onto the denominator. That should be easy to remember. The base goes onto the base of the fraction. The x goes into the numerator of the fraction, and then the new base is anything we want to change it to. Okay, so there's a way to kind of remember that one, but it requires a little bit of memorization. Still, very cool intuition. All right, let's take a look at this one down here. Base switch formula, is this one true? Okay, let's again use it with some numbers. We're going to use c is equal to, what do we say, 2, and x is equal to 8. So we could try this out. This would be log base 2 of 8. Does that equal 1 over log base 8 of 2. All right, let's think to ourselves a little bit here. Well, this side over here definitely has a story. Log base 2 of 8 means what's the power? This is a power finder function. What's the power that raises 2 up to 8? That would be 3. I've got that one down pat. What about over here? This one here would be 1 over the power that raises 8 up to 2. That doesn't make any sense. 8 doesn't raise up to 2. It actually goes down a few levels to get to 2. In fact, it's the cube root of 8 that is 2. So the power would be the cube root, in other words, 1/3. Oh, and sure enough, 3 equals 1 over 1/3. Yeah, we can just flip that thing to the top on the reciprocal, or think of it if you want as multiply by 3 on the numerator and denominator. On the bottom, it'll cancel away, and on the top, we'll be left with 3. Sure enough, this is another true formula. So we have the base switch formula, where you are changing the base and the argument, and in order to do that, you are doing the reciprocal of the logarithm to kind of balance it out there. Okay, interesting. So that's just us saying if I wanted to do the magnitude of raising a base up to an answer, it's going to be the same as the reciprocal of changing the answer to my base. And that should make some sense, because again, if I cube rooted to go up to something, then I would need to do 1/3 of a power, if I cube to go up to something, then I need to do 1/3 of a power, or a cube root to go back down to it. Okay, that's kind of cool. That's a nice idea. We got the base switch formula. What about this addition and subtraction formula? Maybe we're 3 for 3 here. All right, so let's try it. We're gonna do, what did we say? B was going to be equal to 4. So we're gonna write this as just an example, log base 4 of, and then for C, we've got 2 plus x is 8, and we're curious, does this work out where I have log base 4 of 2 plus log base 4 of 8. Okay, log base 4 of 8. Let's try this one out. So we're looking for the power that raises 4 up to 10. Okay, and we're curious, does it work, is it the same thing as the power that raises 4 up to 2? Well, actually, no, the power that raises 4 up to 2. It's actually a fractional power. It's a 1/2 because it takes 4 back down to 2. It's a square root of 4 that gets me to 2. And here I can think of what's log base 4 of 8. Log base 4 of 8. Oh, well, I can think of how do I take 4 and I get it to 8. I would need to square root it first to get it to 2, and then multiply, and do a raise to a 3rd power to bring it back up. So that would actually be plus 3/2. Okay. So sure enough, this would be what? 4/2 would be 2. Okay, so the question is it true that the power finder function, the power that takes 4 and raises it up to 10, would be equal to 2? 4 squared is definitely not 10. Okay, so this is actually not true. This is not a true statement. And this is a one that everybody kind of falls for as they're learning these, especially if they learn them as rules, is they think that if there's addition on the inside, you can do addition on the outside. That's not true. In fact, we actually saw where it was okay to do it, and that was when we were playing all the way up here and we had multiplication on the inside. We could make it addition on the outside, but not if it's addition on the inside. So these aren't just rules that sometimes work and sometimes don't. There's a story that's being violated here. This is a false equation. Okay, so this leaves us with obviously our shortcuts now. So what is it that we have? We have a product shortcut. That was if I have log base b of x times a, that's like growing the magnitude on the inside and then measuring it. I could think of this as the same thing as measuring the magnitudes first and then just adding those magnitudes together. Log base b of a. Good. What about the power shortcut? That was us looking at, oh yeah, where we had log base b of x to the a, and we could think of that as instead of doing the grouping on the inside and then measuring how many zeros I had, I could just do one of the groups and multiply it back out. So that'd be a times the measurement for the magnitude of just the initial group. Okay, so that one makes sense. Quotient shortcut should be the opposite of the product shortcut, and sure enough, that would make sense, because we're going to do log base b of x divided by a would be equal to the opposite of everything that I had above, log base b of x minus now log base b of a, which again should make sense because if I'm decreasing the magnitude on the inside, I should be taking the magnitudes away from each other on the outside. Change of base shortcut, we remember this one. This one is log base b of x could be changed into, and this one here we have a little bit of symmetry in our formula, log base, anything we want to change the base to, c, of the x kind of rises to the top there if you want to think of it visually, and then on the bottom you have log base c of b. And this is again just our way of recognizing that if I can't easily take b up to x, perhaps I can find a middle ground, something that takes c up to x, and then I figure out how many c's there were in b, and then I kind of use that as my middle ground. I ratio them back out. Logarithm of 1. Log base b of 1, what would that be? I'd be looking for the power that takes b up to 1, or down to 1. I guess that would be 0, right? That'd be the exponent that if I raise b to, I would get 1. Okay, so that's equal to 0. So long as we're not doing log base of 0 or anything like that, which isn't a thing. And then logarithm of the base, let's think what that means. Logarithm base b of the base, so that would be log base b of b. We'd be looking for what's the power that raises b to itself? That'd be a power of 1. Okay, so overall not too difficult. Most of these actually parallel quite a few of the exponent rules, because take a look. Remember that if I have x to the a times x to the b, we could think of that as multiplying out x a times and then multiplying it out b times. That was a total of a and b total multiplies, and that looks very similar to our product rule up here, is that I've kind of taken this multiplication and transformed it into addition, or vice versa. So it's almost like, oh, that's right, these are inverses of each other. They're flips of each other. It would make sense that on the inside of the exponent, if I'm doing addition, on the outside, I could think of that as multiplication. Here, on the inside, if I'm thinking of it as multiplication, on the outside, I could think of it as addition. We're inverting the story. We're inverting the process. These are just inverse functions of each other. Okay, so far so good. Let's start using this to see how much power we have when we're trying to solve some of these problems. So what can we find out from this one here? Oh, golly. Well, a couple things stand out to my mind. I can look at this entire thing as saying I've got a lot of multiplication happening on the inside. The 49 and the 7 are definitely catching my eye. Maybe I first expand this whole thing out so that I can look at these piece by piece. So I'll say I've got multiplication on the inside, that'd be addition on the outside using that product shortcut that we found. So I could do log base 7 of x cubed, and then I could even do log base 7 of 5th root of y squared. Okay, let's think through this one. Log base 7 of 49 would be the power I use, or power that raises 7 up to 49, that'd be 2. That works out quite well. What about this next one here? That would be log base 7 of x to the third. What raises 7 up to x to the third? I don't think that one's going to be very nice. I'm just going to leave that one as it is. And what raises 7 up to y squared fifth root? I don't think that's going to happen either. I think we're actually just going to put these back together and call that good. So it'll be 2 plus, and then we'll just kind of recombine that because there wasn't really anything else in there to simplify. So it'd be x cubed, and instead of the plus on the outside, I'll do the multiplication on the inside, fifth root of y squared. And that does look a little bit simpler. At least we were able to kind of pull out that 49 from the inside and make it a 2 on the outside. Okay, so we can just kind of rearrange, we can expand, we can regroup, we can move things around and massage them until we find some simplicity. Okay, what about this next one? I have some division happening on the inside. Maybe I'd like to make that some subtraction happening on the outside using our quotient shortcut. X squared minus 4 would be the thing on the top minus the natural logarithm of 9e to the x cubed. Okay, what can I do from here? I see an e. The e and the natural log make me think that there's something there, but they're being multiplied right now. So maybe I expand this out one more time. Natural logarithm of x squared minus 4. I don't see anything in there that has to do with the base of e, so I'm going to have to leave that one alone, I think. Minus natural logarithm of 9 times e. Oh, we can make that addition. But if I make it addition, I already have a negative attached to the whole natural log. Let's be very careful here, because if I'm going to start to make many negative things, maybe I'll keep it as a bracket. So this would be natural log of 9 plus natural log of e to the x cubed. Okay, so lots going on in there. Now, do we see, again, why it is that I chose to do the brackets? Right now, this here represents something that is on the denominator of the fraction. If I didn't include brackets, then on the next line it would have looked like I just had plus a whole bunch of stuff, and if I had tried to combine it back together, I would have got the wrong visual indicator. That would have needed to go on the numerator. So we're going to do it's everything in the denominator still being grouped here. Alright, still can't do anything with this, still can't do anything with this. This next part looks good. I want to get at that e. There's a power. Well, we have a shortcut for the power. That'd be a natural logarithm of x squared minus 4 minus, maybe I'll distribute this out because the brackets are annoying me, natural logarithm of 9 minus the, I could take the power to the front, that'd be x cubed natural logarithm of e, as just a reminder. And again, this is our power shortcut, so we can go up here and just remind ourselves what the power shortcut was. It says if I have something to a power inside of a logarithm, I can take that power out front in multiplication. And that's because, again, I would have had repeated grouping of my x on the inside. That would have made its magnitude bigger. So why don't I just measure the magnitude once, and then I'll multiply it all at the end to kind of scale it back up again. Well, this does give us a little bit of something or other. Here, we get the natural log of x squared minus 4. Here we have the natural log of 9, a number that we could calculate if we wanted, but it's going to come out to be something nasty, so I might as well just put it back. And then here you've got x cubed, natural logarithm of e. Well, natural log is log base e. What's the thing that raises e up to e? That'd be 1. In other words, this is actually your logarithm of a base shortcut we could apply here. We could just say it's times 1. And all of this can then get combined back in the things that don't simplify. Natural logarithm of the x squared minus 4 divided by 9 goes all back in, and we're left with being able to at least have pulled out that x cubed. So, okay, we were able to get some stuff here. That worked out pretty okay. And take a look at, again, back here, we'll build some of that intuition. Really what we went digging for that e, one of the few things that looked like it would simplify, and it worked that we were able to pull the power out alone. As we're kind of building our intuition, that seems like it passes the general gut check, but maybe we want to go back over our work in a little bit if we feel unsure. All right, I'll trust you to do that one. What about this one right here? Ooh. I see some symmetry. I see a natural logarithm on both sides. If I had just the natural logarithm on both sides, I could say the argument of one was just dead equal to the argument of the other. The 2 in the front doesn't let me do that. Can I take the 2 from the front and put it somewhere else? Well, okay, now I'm thinking. Over here, I had something in the front that I caused, and I pulled it from the exponent. I should be able to then also do that in reverse. That'd be the natural logarithm of x squared. Oh, okay, natural logarithm of x squared equals the natural logarithm of 16. Oh, 16, not 19. Well, that's actually a pretty easy one to solve now, because now I'm just trying to say that whatever's on the inside of my logarithm on the left has to be the same as the logarithm on the right. That's x squared equals 16. And so that would be x is equal to plus or minus 4. And we should be done. And in truth, most of the time we would be, but there's a little bit of a trick here that I want us to be careful of. If you are dealing with a natural logarithm, in fact, any logarithm, keep in mind that negative answers don't work. Okay, and the reason for that is back to the story. If we remember again, kind of that idea of like a logarithm, if you will. So let's do, oh, here we go, a logarithm of, let's try negative 10. So we're trying to look for what's the way that I raise 10 up to negative 10 by exponents? Ooh, actually, I don't think that works. Maybe we'll step away from the logarithm. Let's do it as just the log base 10 example. So if I wanted to rewrite this as an exponent, I'm looking for log base 10 of negative 10, and we're trying to find out what that is. I could rewrite this all as an exponent. This would be a base of 10 to a power of x equals negative 10. So I'm looking to explode my 10 multiple times or collapse my 10 multiple times so that the number of things I get at the end are negative. That's not how exponents work. Again, back to the pay it forward example, one person helps out 3 people. If you go back in time, 3 people came from one person, but at no point did we have negative people. This is actually a nonsensical solution. So it turns out that in this problem down here, if we tried to plug in x equals negative 4, notice how in the beginning I'd be trying to do a natural logarithm of negative 4. That makes no sense. This is what we would call an extraneous solution. In other words, a solution that worked out only because the model we were using as we were solving this thing through gave us a potential solution, and we need to verify to make sure it actually exists. So we have an extraneous solution at negative 4. It's something that we got to from our work, but actually doesn't satisfy the problem, and the only true answer here is x equals 4. Okay, so let's double check that one again. Again, there's lots of ways you can think about that one. If you don't like the story, perhaps we like going back to thinking about the domain when we were graphing it. Exponential graphs look like this. If we inverted that one back in our other lectures, you'll remember that it looked something like this as our logarithm. This is our log graph, which means that the domain is only in the positive numbers, in the same way that exponents only get me positive answers when I've got a positive base. So in this situation, I can't have a negative x value and try to find out a place down here where it intersects the logarithm. So whenever you are working with logarithms, we have to be very careful that the numbers that we are plugging into logarithms are in fact positive. Okay, enough beating on that point. Let's try some of these ones here. Now, keep in mind that for a lot of these numerical ones, we're going to be wanting to use our calculator, and our calculator sometimes has the ability to do different bases, but if it doesn't have the ability to do different bases, we always have that change of base formula in our back pocket. So let's play around with this one here. I have an exponent I'd like to solve out for. So actually, why don't we just let that drive the situation? Let's make it so that I'm going to do log base 2 of the left-hand side. That'd be 2 to the x plus 1. And we'll balance that off with doing the logarithm base 2 of the right-hand side. So essentially what we're doing is we're saying these two statements are true, wonderful, and I'm saying, well, if they are in fact true, if they are in fact the same, then whatever magnitude takes 2 up to the left-hand side should be the same as the magnitude that takes 2 up to the right-hand side. And it flows from logic. That would be absolutely true. Well, whatever takes 2 up to 2 to the x plus 1 would just be x plus 1. And you could look at it that way. You could also kind of give yourself a little bit of a half step if that feels weird. You could think of grabbing that power and pulling it to the front using the power shortcut we were talking about. That would leave us with log base 2 of 2. And what raises 2 up to 2? 1. So it'd be 1 times x plus 1. Either way that we think about this one, we're eventually going to get to x plus 1, which was the digging we were going for when we solved this when we were attempting this problem. We wanted to get at that exponent. Logarithms allow us to do that. They're the reverse of exponents. They undo exponentials. Okay, and then on the right-hand side, we would still have log base 2 of 3. And then we have, let's see, we could solve for x. X would just be equal to then log base 2 of 3 minus 1. Now, suppose we actually wanted to know the numeric value for this one. This actually is going to be the simplest way we can express the answer, but let's suppose that we wanted to kind of get, again, building some intuition. We want to know exactly what this number would have been. I could pull over my calculator, we could take a look. Well, if I'm looking at a simple calculator, you were going to notice that I don't have a log base 2 button. I have a log button, but we know that log without any kind of like subscript just means log base 10. How could I use this calculator, or do I have to go buy a new one? Well, we could actually use the change of base formula. I've got a base of 2, it's making me unhappy, I can change it. We could actually rewrite this entire thing where now instead of log base 2 of 3, maybe I'll write this as log base, my nice happy base, log base 10 of 3 divided by log base 10 of 2. Minus 1. Now I should have everything that my calculator can actually help me with. I can do the log base 10 of 3, that gets me this number. I could divide that by the log base 10 of 2, and that would get me this number right here. And then I could subtract 1, and it looks like it gets me something a little bit over a half, so about 0.58-ish. So 0.58-ish, little squiggly equals, is a way for us to know that what we're doing here still is just numbers. And we can again go back to the interpretation of this. It looks like if I put 0.58 in as x, that'd be 0.58 plus 1, that'd be 1.58, and so it looks like it's saying that if I have 2 and I raise it to something that's about a 3/2 power, I should get 3. Let's double check that. If I have 2 and I raise it to something that is about a 3/2 power, let's do 3 divided by 2, double check that that looks good. 2 to the 3/2 power, that'd be 2 to the 1/2 power. That should get something close to 3. Okay, yeah, sure enough, generally kind of close to 3. So not bad. Maybe a little bit higher, right? We could do 2 to the, maybe not 3/2 power, we could do to the 1.58 power. And that should get me even closer to 3. And there we have it. So all we're talking about is the number of magnitudes. How many times do I need to multiply 2 by itself? Looks like 1.5-ish times would make that work. Okay, what about the next one? Well, now I have 2 different bases. Which one do I start with? I guess whichever one I want, why not? Okay, let's do log base 7 of both sides. That should hopefully be able to cancel out this 7 over here. And then we'll do log base 7 on the right hand side to make it still balanced. So again, the story here is how many magnitudes do I have of 7 that raise me up to 7 to the x plus 3? That would be x plus 3. And over here, that would be how many 7s do I have that raise me up to everything here? I don't know, difficult. We'll leave it as it is. Can we do anything else here? Oh, I have an exponent. I can pull the exponent out front. That would be 2 minus x being pulled out front of this logarithm base 7 of 4. And that'd be equal to x plus 3. Okay. What do I have there? I mean, I guess we have some more manipulations we could do. I don't see a great way to tackle this one. I was thinking about maybe dividing both sides by 2 minus x, but then I have x in a couple of different places. Maybe I need to distribute this as if it's just a number, because it is. Okay, that'd be x plus 3 equals 2 log base 7 of x minus log base 7. Oh, sorry. 2 log base 7 of 4. There we are. 2 log base 7 of 4. Minus x log base 7 of 4. Now I can get my x's on one side and all my numbers on the other. So that would be x would stay on the left. I would add my x log base 7 of 4 to both sides. I would still have the plus 3 over there, and that would be equal to 2 log base 7 of 4. And then I guess we could get the 3 out of the way, try to get the x's alone. So I had x plus x log base 7 of 4 equals 2 log base 7 of 4 minus 3. Maybe I'll use parentheses here to make sure that I'm keeping everything nice and grouped, not getting anything confused. I have x's in 2 different places. It's being multiplied 2 different places. We could factor it. We could factor it out. I could make this x on the outside. That'd be 1 plus log base 7 of 4 equals 2 log base 7 of 4 minus 3. And now to get x alone, I need to get rid of this whole parenthesis thing. I'll divide both sides. That gets me x equals 2 log base 7 of 4 minus 3 divided by 1 plus log base 7 of 4. And not a pretty answer, but it did work. So do we have a method to make this happen? I mean, this method works, and this was just the one that I chose when I tried to do a log base 7 on both sides. In fact, I think I could have just done log base 4 on both sides, and I probably would have been able to get to something similar. I don't really see anything here that's going to be able to simplify within the expression, because I could maybe put the 2 here up in an exponent. I could make this 4... Oh, I could actually simplify that up a little bit. I've got 2 in front. I could, as just kind of extra here, do x equals, instead of 2 times logarithm, that should be a power formula, or power shortcut, so I can make log base 7 of 4 squared. That'd be 16. Log base 7 of 16 minus 3 over 1 plus log base 7 of 4. And then I think that's about as far as we're going to get. There's not going to be an easy way to raise 7 up to 4, so the logarithm on the bottom is stuck. I can't combine it with the addition on the bottom because this other part doesn't have a logarithm. Same thing with the top. I'll make this grouped so that it really stays clear that this is a log base 7 of 16. The minus 3 is on the outside. I think we've got our most simplified answer. And there probably would be another one with a log base 4 if we had started it that way. Okay. Good. So a little bit difficult. We're pulling in a lot of different tools. The logarithm is definitely a weird visual, but the process should feel pretty okay. All right, let's do a few more of these ones and call it good. So solve each equation. Let's round to 4 decimal places. This means that we have permission to use our calculator. I have an e on the outside. Maybe I don't like having that multiplication on the front. Well, I can't do anything with it yet, but if I have the e is really the bothersome thing, then let's try a natural log, a log base e. So we'll do natural log of 25 times e to the x minus 5 equals 17. That would be, let's see, multiplication inside the logarithm could be made addition. Natural logarithm of 25 plus the natural logarithm of e to the x minus 5 equals 17. This is just a number. I'll save it for later. This natural log of e kind of cancels away and leaves me with x minus 15. And then I think we would just say I have the 17 on the outside. Let's get x alone. I think that's just going to be adding 15 to both sides would be 32. And then I would subtract the natural logarithm of 25. And we could throw that in our calculator. So let's pull up the calculator. That would be 32 minus the natural logarithm of 25 would equal about 4 decimal places, 2.7811. 2.7811. Okay. And I'll leave the rest of these here for you to kind of play around with to make sure that you have a good understanding of the process. But what we're playing with is nothing that's too crazy. It's just everything we've been dealing with algebra inside of a new model. But all of the logic still holds. It still follows a story. And of course, if you have any questions at any time, pull me over and we'll talk through it together.